well, I have the pleasure to give you, in fact, two presentations, two successive presentations. The first one should have been given by Pierre Mills, but unfortunately he was not able to come, and so I will. So the idea is to have a general framework to describe two different systems of non-Brownian particles, whether dry grains or dense suspensions immersed in a viscous fluid. So I'm considering homogeneous shear flow of assemblies of grains of size D, possibly immersed in a viscous fluid of liquid viscosity eta L. The particle may be frictional or not. We see that it has some importance. And it is submitted to shear. So we control the shear rate, gamma dot, and we control the pressure, P. And the system is described, the shear state is described by the solid fraction, phi, and the effective friction, mu, ratio of shear stress and pressure. And there is also the jam state, which is also considered the critical state of the system, which is denoted by a star. So this jam state will be defined by solid fraction phi star and effective friction mu star, which depend on the friction between grains mu g. So both systems can be described by dimensionless number built from the combination of the two typical time in the system, the shear time, and time associated to inertia in dry granular systems, or viscous time in dense suspension. And from that, so you have the inertial number Ig for granular systems, and a viscous number Is, called here denoted Is, in dense suspension. And then, so the shear state will be described by the dependency of solid fraction and effective friction on those dimensionless numbers, as previously discussed. And here examples of results for both kind of systems. On the left for dry grains, on the right for suspensions. So in 2D or 3D, and for frictional or frictionless grains. So there are results by Pierre-Emmanuel Pénaud and Jean-Noël Roux. There are results by Saïd Ramzé. Those results come from discrete numerical simulations. And I also show results from the experiment of Boyer, Olivier Pouliquin, and Elisabeth Guazelli. So those curves show that it's possible to describe the shear state through the dependency of phi on mu as a function of those inertial or viscous number. And then, well, question is to discuss those constitutive laws. And here I introduce an idea which is the relaxation from the shear state to the jam state. So when suddenly cutting off the shear stress while maintaining the normal stress. So the system will transit from system with shear rate gamma dot on the solid fraction phi to a system where the shear rate equals to 0 and solid fraction phi star. And for that, there will be a characteristic time tau. And then defining this characteristic time, we introduce a time evolution for the solid fraction. The idea is that you can share the evolution of the solid fraction as a first term introducing this relaxation time, and another term which so a term which would be proportional to the shear rate, proportional to the solid fraction, and with a prefactor A. This term would be associated to the tendency of the system to dilate when you have dissipative interaction between particles. So for instance, here it's a very schematic view for a dense, for a dilute suspension where you have a collision between the gray and the black particles, and after the collision, the black particle has changes its position by an interval delta A. So the parameter A would be a measure of the relative increase, the dilatancy of the system. So it should be of order of some tenth. So then, if I consider this equation on the go to steady state, this provides me an equation for the dependency of the solid fraction as a function of the shear rate and the relaxation time. So this is equivalent to an equation of state for the material, since it relates solid fraction, shear rate, and within the relaxation time, there is also the pressure, which is hidden. So this is our equation of state for the system. So for both systems, and so now I have to say something about the relaxation time. So one idea could be to consider this relaxation time as the typical inertial or viscous time which was introduced to define inertial or viscous number. But rather than considering this this time, we rather propose to consider it as sorry, there is a mistake in my transparency. We rather consider it as the ratio of the effective viscosity eta divided by the pressure P, where the effective viscosity, is is defined as in this expression. So the shear stress is given as let's say the shear stress in the critical state plus a viscous contribution, which defines the effective viscosity. So, yes, sorry. It's just just 2 equals eta divided by P. I'm sorry. So, if I use this definition, you can remark that mu is, so the effective friction is also equal to mu star plus gamma dot tau, while we saw previously that phi star was equal to while phi was equal to phi star minus r phi gamma dot tau. So we notice that if this idea is consistent, we should have the same kind of dependency for solid fraction on effective friction. And indeed, there are some hints which I will detail, but for instance, we should recover a simple relation between effective friction and solid fraction as shown here, as observed in some numerical simulations. So this seems to be a possible choice for the relaxation time. But I want to go further and noticing that the analysis of the constitutive law seems to identify scaling laws for the dependency of solid fraction on effective friction as a function of inertial or viscous number. And here is a tentative summary of some results for the exponent alpha and beta, which happens in which are measured in simulations for dry grains, or in simulation or experiments in for dense suspensions. And so some there are various results here, but some approximative conclusions we could find from those results is that it seems that the two exponents alpha and beta are close, not always equal, but they are in some cases they're very close, like in three-dimensional frictionless dry grains. In other cases, they are close. There might be a small influence of dimension, 2D or 3D, but essentially there is a strong influence of friction between grains. For instance, so those exponents vary from around 0.4 for frictionless grains to close to 1 for frictional grains. So if I take the previous ID, and if I look at the conclusions or the consequences for the expression of the shear stress, this tells us that the viscous part of the shear stress for grain or suspensions may be written as a product of, well, the term that can be simply written from dimensional analysis, so OG, D squared, gamma dot squared for grains, or eta L gamma dot for suspensions, times a function of the solid fraction, which is diverging near jamming, and with an exponent which is related to the exponent previously shown. And then, if we take the results that alpha is approximately equal to beta, we have these conclusions for dry grains, for frictionless dry grains with alpha and beta close to 0.4. This would tell us that the divergency as a function of friction would be with a power of 4, with an exponent 4, while for frictional grains the divergency would be with an exponent 1, and for dense suspensions the divergency would be with an exponent 1. So so the test of consistency of the model, well, VID leads to this conclusion, and so there are surprising or, well, appealing questions, like the fact that the exponent for the dependency on solid fraction is very different when introducing friction, and for the viscosity here, well, it can be discussed because there are results showing an exponent rather of the order of 2 or larger than 2, so it's not completely. And so I go to conclusions which are rather questions at this stage. So are there really such scaling laws for effective friction on the solid fraction? How do they depend on the friction between grains, for instance, on dimension? Is there a if we introduce a relaxation time for solid fraction, is it really connected to viscosity? I've not proposed at all any real microscopic interpretation for the equation of state. We may try through Boltzmann equation approach. I've chosen not to present it because I'm not completely confident with that. Yes. What about the viscous shear stress? How to interpret the exponent which are found at the end in the viscous shear stress? Is it associated to a correlation length, size of clusters? Well, and why is there such a strong influence of friction? So, thank you for your attention.
This reminds me of dilatancy, like Reynolds dilatancy, and you've not used that word. So is there a reason why? And would, like, I don't know if there's work done already on Reynolds dilatancy, but would that, I suspect it to be very different when you have friction or not, and when you have interstitial liquid or not. And I wonder if it might be a way, or I don't know, give a clue to explain all the different things you have in the channel.
well, I've not. Well, so Reynolds dilatancy would be so the dilatancy which you observe when you start from arrested state and when you start to shear it. And here I'm rather considering the problem in the other direction. I have dilatancy. The equation of state is an equation for dynamic dilatancy of the system. Well, at this stage, I do not know how to make the connection between both physical mechanisms.
At this point, we need to move on this part of the presentation. Are you doing the second presentation as well? You can hold those to your questions to the later part. So we stay on time.